Alright, so we're recording now. Is anybody in there? Can somebody just jump on the Teams meeting and just tell me what you see? Anyone? I'm trying to share from the camera app. Apparently that's the way to do it. Oh, there we go. What am I actually sharing there? If I move this, does it disappear? Okay, so I need to do it like that. All right, that'll work. Okay, so power, right. So power is a function of the other properties that we talked about yesterday, specifically current and voltage. So power is how we generally measure electricity, right? This is what you pay for when you pay for your power. You're paying for power. So we're supplied a voltage, and then we draw current off that. We multiply our power by our current. We've got a little meter in the switchboard that does that, and that's how the power company charges us. Is anyone else seeing the camera on that meeting flipped? It's not going to work, is it? It shouldn't be sharing the screen, it should be sharing that window. But either way it works. If it works, it works, but it's no good if it's backwards.
Because like if I minimize this, last time it was still all video. I can still come up with video, but now it's...
Okay, then let's scrap that and try again with just turning the camera on. It would just mean that the camera won't be full screen. Is that better? Is it saying? Yeah, okay. Okay.
Hopefully it'll just leave it.
Oh, possibly. Right, so power is defined as the rate of doing work. There's a few things to unpick there. When we're talking about power, it doesn't just specifically refer to electrical power. Power can be a measure of any work that's done. So we have mechanical power, electrical power, so on and so forth, right? When we talk about when they talk about the output of a cyclist in the Tour de France, they're talking about the number of watts per kilogram that a cyclist can generate. So watts are our measure of power, right? So it doesn't just have to be electrical. But a watt is a watt is a watt. So a watt of electrical power is the same as a watt of human power is the same as a watt of mechanical power. So this is a very broad, what do you call it, measurement or unit. And it's a rate of doing work. So a watt has a time factor in it. Okay, so power is energy times time. So the amount of energy that I'm producing, or the amount of energy that's being consumed, times the amount of time that you're using it for. So power is a rate. It's just like, so if we think about it like kilometers per hour. So a watt is like a kilometer per hour. Now, we can all understand what kilometers per hour means, right? But we wouldn't say, oh, how far did you have to drive today? You wouldn't say, oh, 50 kilometers per hour. It doesn't make sense, right? It doesn't make sense. So when we talk about power, if I said, oh, say, how much power did you use? Oh, 40 watts. That would be the same thing. That would be like saying 40 kilometers per hour. It doesn't make sense. Unless it's got a time factor in it, it doesn't mean anything. So when we pay for power, we pay for kilowatt hours. So 1 kilowatt hour would be using a kilowatt for an hour. Does that make sense? So then if we refer back to that analogy of kilometers per hour, if somebody said, how far did you drive today? And say 50 kilometers an hour for 1 hour. I mean, that would be a weird thing to say, but I would be able to work out how far you've traveled, right? 50 kilometers an hour for 1 hour. Oh, 50 kilometers, that makes sense now. So that unit of measurement, a watt, is a rate of using power. It's a speed. So unless we have a time factor in there as well, it doesn't make any sense. Or we could talk about it as an instantaneous measurement, right? So it would be the rate of using power. So if we talk about a 2.5 kilowatt heater, that means that it's going to consume 2.5 kilowatts per unit of time, or as an instantaneous measurement. So if I use that heater for 1 hour, then I would have to pay for 2.5 kilowatt hours. Symbol of power is P, capital P, and the unit is a watt. So just see. 1 watt of power is produced in an electric circuit when a voltage of 1 volt causes a current of 1 amp to flow. So if you look at that, you realize that, well, there's some arbitrariness about those measurements, right? And in fact, that's one of the cool things about electricity, is that when people have discovered it and then started putting units on it and going voltage and current and stuff like that, they just made them up. Oh, this much electrons flowing, we're just going to call that 1 amp. And then this much potential difference, we're going to call that 1 volt. And then we need a measurement of the rate of use. Oh, well, let's just multiply them together, and we'll call that 1 watt. And there we go. So all of these things fit nicely together because we just decided that's what they are. It's not like, get a bunch of bananas. I can't just say 1 bunch of bananas is 7. Well, it is what it is. It's however many bananas there are in the bunch. But with our electrical quantities, we've just made it up, which makes it fit much easier, right? We don't have to deal with decimals or pi or anything like that. It's just what we decided it was. So 1 volt causes a current of 1 amp to flow. If we have 1 volt causing a current of 1 amp to flow, that's going to be consuming 1 watt of power. Make sense? And then we can postulate from that obviously the way we work out power is volts times amps. Whatever my voltage is, multiplied by the current, is my power. Now in this case, 1 times 1, 1. If I had 2 volts and I had 1 amp, it's going to be 2 watts. Real simple, real easy. I just multiply my voltage and my current, and I get my power. Except for later on when it gets real complicated, but that's not till next semester, so don't worry about it. We start adding in capacitors and stuff like that, then it does really screwy things to our power. So here are our formulas here. Let's have a look at that. Power equals voltage times current, as I just said. Power equals voltage times current. But power also can be V squared over R or I squared times R. How do we arrive at those formulas? They're all based on the first one. Now, yesterday we had that triangle, V equals IR, I equals V over R. It's the same sort of thing. And now we've got V squared over R and I squared times R equals power. And we haven't got any mention of resistance up here. So where does it come from down here? Any ideas? Nailed it. So in this formula here, I don't have current, right? So presumably I would use this one if I had voltage and I had resistance. Now I could use voltage and resistance to work out my current, right? That makes sense? Because I know that I equals V over R. V over R. And then if power equals V times I, but I don't have I could work it out using V over R, or I could just skip that step altogether and just substitute into my formula V over R. Right? That equals I. Does that make sense? So V times V over R being I, that means this formula here, V times V over R, is the same as V times I. Yep. And then I can just simplify that formula a little bit because I got V times V, which is V squared, divided by R. So then we have V squared over R. Easy, simple. And so for this one here, I don't have the voltage. I've got current and resistance. How do I work out power? Well, let's do it step by step. Which formula am I going to be looking for? If we're doing Ohm's law. And I don't have the voltage, right? Yeah, what was that, Jake? V equals I times R. And then P equals I times V. And my V is going to be I times R. That's V. Then I times I would be I squared times R. I squared times R is the same as V equals IR. Or sorry, it's the same as P equals V times I. So this here, those two there are the same as this. It's just using our Ohm's law formula to work out either voltage or current, depending on which one I don't have. So I could do this either way, right? So if I had the voltage and the resistance on the circuit, but I didn't know what the current was, then I could work out the current using voltage and resistance, and then use that with the voltage to work out my power. So that's simple. Same down the bottom one, if I had the current and the resistance, then I could use those two things to work out the voltage, and then multiply that by the current to work out my power. Or, as I say, you can just skip that step and use one of those two formulas. But if that's starting to feel a little bit confusing and your brain is starting to swim, then we just stick to this one and our Ohm's law, and it's going to do the same job. Does that make sense? Okay, so let's do a little calculation. So we've got a series circuit diagram below. We need to calculate the following. Total circuit resistance, we did that yesterday. For a series circuit, we just add the resistances together. The total circuit current. So what's the current flowing in the circuit? We do that by dividing our supply voltage by the total resistance. That's going to give us our total current. Power in the 3 ohm resistor. So what information do we know about that 3 ohm resistor then that's going to help us to work out the power? Which of those formulas am I going to use if I want to work out the power in the 3 ohm resistor? Come on the last slide you all told me it made sense. B squared over R. Any other guesses? What voltage would I use then?
100 squared.
So I could do that. I could use 100 squared divided by the resistance, but that would give me the total power for the circuit. If I used 100 squared divided by 3, it's going to give me an incorrect answer. Does anyone know why? What, seen it? Why would that be wrong? In a series circuit, do I see the full voltage, the supply voltage of the circuit on every resistor? No. So we know that it's going to be some voltage on this one and some voltage on this one, right? If we measure across the two, we're going to see 100. If I measure here, I'll get a different value, and if I measure here, I'll get a different value. Remember, those two values, the two voltages, will add up to 100. So if I use the 100 and the total resistance, that'll tell me the total power in the circuit. That makes sense. But if I want the individual power of the individual resistors, I'm going to need to use the individual voltages. But I don't know what those are. Now, again, I could work them out, right? I know what the current is now, because we did total circuit current by doing V divided by total resistance. But I don't necessarily know what that voltage is. So I can work that out, but I don't have to. I know what the current is, and in a series circuit, the current's going to be the same all the way through. And I know what the resistance is of that resistor, so I can use I squared times R. I squared times R for this one, I squared times R for this one. And it's going to give me the answer. And then I can work out total power. Now there's a couple of ways I can work out total power. Total power is going to be total power consumed by each of the resistors together. So I could just add those two numbers together, or I could do what we looked at before, just do voltage times total current, and that should give me the same number. We can prove all these things. We can go through the working out and prove them all. But I want you to do that first. So go through, do A, B, C, D, and E. And then we'll have a crack at it on the board and see a number of different ways. It's good to see those different ways because it starts to show how they're all the same.
What do you see? 3.3 kilowatts. Which is the same. Done. Total now. So I just need here. I did but
Must be it up.
Yep.
Currently used.
was basically voltage divided by
Current is going to be the same. Current is our rate. I just let the hose at 2 different points. This is the one you're going to get.
So I should just
Yeah. Total current. All right, so let's have a look at that. Let's have a look at that. So let's take a little time and we'll run through every permutation that we can think of for this question. So, first answer should be pretty simple. How do we calculate resistance in a series circuit? Ohm's law. Total resistance in a series circuit, add them together. So it'll be 3 plus 6. It's 9 ohms. Nice and easy. B, that's nearly as simple. We're just going to use Ohm's law. We're trying to work out total circuit current. So how am I going to work that out? I equals V over R. So our voltage will be 100. So total voltage, total resistance is 9. So my total current is going to be 11.1 amps. Everyone agree with that one? Yeah. So that's my total current in the circuit. But remember, in a series circuit, the current will be the same all the way through. We think about our resistors as restrictions in my hose. And so no part of the hose is going to allow more water through than the smallest restriction or the total restrictions in the pipe, right? Remember that one? That makes sense. I can't have 10 litres per minute up to here and then only 3 litres per minute through there, because then where does the other 7 litres per minute go? So if I restrict this down to 3 litres per minute, then there's only going to be 3 litres per minute in the whole thing. Current will always be the same in a series circuit. Okay, so those ones are easy. Right, power now gets a little bit trickier. The power in the 3 ohm resistor. Again, so to work out power, I need to do volts times amps. Volts times amps, that's our master formula for power. But I don't know the voltage. I've got one voltage, that's 100 volts. Can I use 100 volts for this formula here? Can I use 100 volts? No. If I use 100 volts, if I use V times I, 100 is power, 100 is voltage, and 11.1 is power, what will that actually give me? What am I working out there? Total power in the circuit. It's not going to tell me that the power in that resistor, it's going to tell me the total power in the circuit, because I'm using the total voltage or supply voltage and the total current. So that's good. We can come back to that later because that'll be useful. So if I do V times I, that'll be 100 times 11.1, which would be 1111.1, presumably onwards and onwards. So we'll just put a box around that one and we'll come back afterwards. Okay, but we don't want to know that yet. We want to know the power in the 3 ohm resistor. So again, I could work out that voltage, right? We did that yesterday. So how would I work out the voltage? How would I work out the volt drop across that resistor? V equals I times R. Good, yes. I will use my current and my resistance to work out what V is across that resistor, right? But we don't have to do that because we already have the current and the resistance, and we have a formula that will tell us that, right? What is that formula for power if I only have current and resistance? I squared times R. Okay, so let's look at that. P equals I squared times R. And my I is what? 11.1 squared times R, the resistance is 3. So 11.1 squared times 3 is 370 watts. Does that make sense so far? But let's do it the other way just to check, just to prove that I'm not lying. So if I wanted to work out the voltage on that resistor, how would I do it? I times R. What do I use for I? 11.1. And what do I use for R? 3. What does that equal? 33.3. And now we said that, so that's going to be our voltage, that's our volt drop across that resistor, right? So now I know the volt drop on that resistor, then I could just use V times I for my power, right? So then P equals V times I will use 33.3 as my voltage and 11.1 as my current. What does that equal? Is that a calculator? 369. So we've done that 2 different ways, we've got the same answer. Or more or less, there's a little bit of rounding in there because we're not using the full 3.33333 or 1.11111. But we can see that's the same answer, right? It's the same answer because I've done the same thing, just using slightly different steps. Like I said, if we go I squared R, what we're doing is we're working out the voltage inside that formula. And then we multiply by the current. But here we've just separated it out. So we've used I times R to work out the voltage, and then use that voltage with the current to work out our power, and we get the same answer. Isn't that beautiful? So symmetrical. No. One day you'll be cool like me, and you'll love this stuff. So, if I want to do the power of the 6 ohm resistor, what am I going to do? What formula should I use? Same thing. E equals I squared times R, which equals 11.1 squared times 6 this time, right? What's my answer? 740. Okay. Does anybody want me to go through the voltage calculation for this one as well? Now, look, I mean, if we wanted to do that, there's lots of ways we could do it, right? We could copy the same formula here, and we go V equals I times R, so we go 11.1 times, instead of 3, it will be 6. And it's going to give me my volt drop, and then I use the same formula here, but instead of 33.3, I'll use 66.6, because that's going to be my answer for the voltage, times 11, and it's going to equal 740. 739. And there's another way I could do it, right? Because now I know that all the volt drops in a circuit, on a series circuit, add up to what? Total voltage. So then I could just use that to tell me the voltage on the 6 ohm resistor by just going 100 minus 33.3, right? And what will I get? 66.6666, and that's my voltage, and I multiply it by the current, and I get the same answer again. So all of these things tie together, right? None of this stuff sits in isolation. So once we get the hang of this, this is how you check yourself, did I get the right answer? So now E is going to be total power, and just on the variables that we've already worked out, there's 2 ways for me to do this. Somebody tell me one. We already did one, yes. We did it at the top here, right? We did total voltage times total current to give us 1111.1. What would be the second method? Can anyone see the second method that I could use to work out total power if I hadn't already done that based on what the other stuff that I've done? If I add them together, what do I get if I add 369 and 740? I just do P1 plus P2, so that'll be 369 plus 740, and that equals, what does it actually equal if we add it? But if I just add those two numbers, it'd be 1,109. Yeah. If I use 369 and 740, I get 1,109. Now, there's rounding errors in there, that's fine. Whenever you answer a question like this in Canvas, it always gives a range. So the answer to that, if it was a Canvas test, would probably be 1,110 plus or minus 10 or something like that. But even if you screw your rounding up massively, it's still going to give you the right answer. But we can see there that if I did V times I got 111, 1111.1, so on and so on. Then if I work out the individual power on each of those resistors and add them together, I get more or less the same answer. So that proves that I did it right. If you didn't work through any of this correctly, these answers aren't going to be correct, and when I add them together, I'm not going to get this. So there'll be a difference between this one and this one, and then I know I've done something wrong. And as we add more resistors and parallel and series circuits and stuff like that, we'll start to see more and more of that different methods of doing it, and therefore different ways of checking that we've got the right answer. Okay, so it makes sense to everybody. Comfortable with that? I mean, broadly speaking, like nobody's sitting there going, I don't know any of this, I don't know what you're talking about. What is power? What is ohms? That's fine, because we're going to have plenty of practice. Okay, so now we've got a parallel circuit. Is it going to be different? Yes? No? Different? No? It will be different. Why will it be different? Yes. Okay. So, I think the simplest way for me to understand this, because the parallel circuit is probably a little bit more complicated. Remember that in our parallel circuit, the voltage across each resistor is going to be the same, right? Because look, this is my 100 volt side here, and that's my 0 volt side here. Then I know everything that's connected to that 100 volt side must be 100. Everything that's connected to the 0 volt side must be 0. Therefore, I've got 100 volts across each of those resistors, right? I know what the resistance is because it's given to me. It says at 175, 50, 7. But what's going to be different between this circuit and the last one is how we work out the current. So the easiest way for me to understand this is when I think about calculating power, I'm using the voltage, current, and resistance of each individual resistor. So I'm never going to use, on that series circuit, I'm never going to use 100 volts because that's not the voltage that's on that resistor. Now, like we said, we don't necessarily need the voltage, but if I had it, that's not the voltage that's on that resistor. So if I wanted to work this out, I need to know, well, what's the voltage on that resistor? What is the current that's flowing through that resistor? On our series circuit, the current flowing through that resistor will be the same as every other resistor in that circuit because they're in series. The current is the same. But if I'm working out the power on that resistor, I want to know what is the voltage on that resistor and what is the current. In a parallel circuit, we can see the voltage is going to be the same at every point in that circuit, or every resistor will have the same voltage across it. But because we've got those branching pathways, we're going to have a different current. We're going to have a total current, and then we're going to have 3 individual currents that should all add together to be our total current, right? Just like our volt drops in a series circuit add together to total voltage, all our currents in a parallel circuit should add together to give our total current. Make sense? So if I wanted to work out this one, power in the 175 ohm resistor, what would I do first? I need at least 2 pieces of information about any of those resistors to work out the power, right? Go, Ollie. $100 squared divided by 175. Does everyone agree with that? see your blank faces.
You can see, yeah, that's
See, I can see. Neither agree or disagree, because I don't know what you're talking about. He's right. He's right, because I need at least 2 pieces of information about that resistor to give me to be able to work out power. Right? I need at least 2 of voltage, current, and resistance. Like C1, I've got 175. That's easy because it's right there. The other piece of information, minimum, if I've got all 3, then there's different ways I can do it. That makes it easier. But if I've only got 2, what's my second piece of information in a parallel circuit? Voltage or current? Voltage. And I know the voltage right off the bat. Why do I know the voltage? Because they're all the same. I'm going to have 100 volts on each of those resistors. So now I know I've got, for the top resistor, I've got 100 volts there, and it's 175 ohms. So I'm going to use the formula P equals V squared over R. Then remember, this is only, all we're doing here is we're putting that calculation for current into our calculation for current power, so we can skip a step. I could still work out the current if I wanted to. Let's go V over R. And it's going to give me current. It's going to come up with the same answer as V squared over R, right? So that would be 100 squared divided by 175, which equals 57.14 watts. Yes? Great. Okay, let's do the next one. So for the second one, we're going to use what? Exactly the same formula. Exactly the same formula. We're just going to change one of the values. Which value will we be changing? The resistor. The resistor changes from 175 to 50 watts, which means our wattage will change to 200 watts. And then for the third one, I change that again. It's going to be 7 ohms, which means my wattage will now be what? 1428. Does it make sense? Happy with that? Okay, now here's an interesting thing. On that last question, everyone's written down the answers. There's a 3 ohm and a 6 ohm resistor, right? Which one is burning the most power? The 6 ohm. The 6 ohm resistor. Now on the 3 ohm resistor we had 370 watts. On the 6 ohm resistor we had 740, right? Okay, now look at this one. Which one is burning the most power? The lowest resistor. How does that work? So why is it different in the series circuit?
It's getting 100 volts.
Because it's getting 100 volts, and that means that it's going to have a greater current draw. The lower that resistance, the bigger the current draw, and therefore because they've all got the same voltage, then the one with the biggest current draw gets the most power. Makes sense? Why? On a series circuit, why is it different on a series circuit? It's only one current, right? But each of those resistors has a different voltage, and the one that is the biggest resistance is going to grab the most volts. So when we do our calculation, volts times amps, the current will be the same, but the bigger resistor has the most voltage, so it's going to burn the most. It's going to burn the most power. A series and parallel circuit, then the way that our power is going to be more on the lower one for a parallel, and it's going to be more on the higher one on a series circuit. If we wanted to work out the total power, we do the same thing. We do the same thing as we did before, we just add them all together. It doesn't matter. For a series and parallel circuit, when we're adding the power, it doesn't matter if we, It doesn't matter if it's series or parallel, we're going to add those powers together. Why? Because when we talk about power, we're talking about the individual power consumed in that resistor. And the fact that voltage might change or current might change, that's already been taken into account when we work out the power, right? So we just add them together. Whatever the power draws are, it's going to give us that total power. So that means that we've now got at least one way to work out our total power, which will be what? Add them all together. Yep. So what would that equal? So total power equals P1 plus P2 plus P3. 1685. Yeah? Good? Happy? Just add them together. Is there another way for me to work out the total power? Yeah. How would I do that? Ooh. Would it be the same? If I had all those, it's a good question. If I had that same three resistors and I put them all in series, is my power consumption going to be the same? No. Power consumption will be different. Actually, that's the principle behind like a 3-heat switch, right? You know, in an electric blanket, you've got 1, 2, 3, and you get different heats on them. Actually, that blanket's got 2 heating elements in it, and it depends. So on 1, you've got 1 element working. On 2, you've got the 2 elements in series, and on 3, you've got the 2 elements in parallel. So, and then the heat that's generated, that's power, right? That's exactly what power is, how much heat it's going to put out. Then when we go on 3, that's because we've got the two heating elements, which in this example are just resistors, and we're going to get more power out of it. So we're not going to put them in series, we're going to leave the circuit as it is. What's the other way that I can work out the total power then? Total resistance, right. Well, our total power is going to be, our total power again is a function of our total voltage, which we know is 100, and our total current. Yeah? So we can work out, well, now we've got lots of different ways, right? So I could work out what my total current is. I could do that by, so it says here, work out the current in each branch. So I can work out total current by working out the current in each branch and adding them together, and then use volts times amps, total voltage times total current. Or I could work out the total resistance on the whole circuit using now parallel resistance formula. And then I go V squared over R again, power equals V squared over R, so I'd have 100 squared divided by the total resistance. Or of course I could do as we just did and add them all together. Let's do all 3, or let's do the other 2. See what we can come up with. So we start, what did we get when we added them together? 1685. So that's our starting point. We already know the answer. We're just going to investigate different ways to do it. So let's do your way first, Bailey. So we're going to do P equals V squared divided by R. But we need to know what this R is, right? And what's our formula for resistance in a parallel circuit? Or if we do it this way, 1 to the negative 1 plus 2 to the negative 1 plus 3 to the negative 1, negative 1 at the end, right? Oh, bracket there. You do? No, maybe not on your calculator, but I promise that some calculators won't work it out properly without. Why? How are you going to do it?
I just put bracket 165 for the current one, plus 50 negative 1 plus 2 negative 1 bracket negative 1.
Alright, so you're taking out all of these ones.
Yeah.
Yeah. And it gives you the same answer?
Yeah.
I believe you, but I don't think every calculator will do that. So
managed by me, so they do it.
Okay. Oh, I don't know this calculator. Shit. Try this one. So what was the answer that you got?
Hey, what's the next one? Oh, no, that's where I got.
For resistance.
Oh, yeah, no. Right, so, yeah.
5.9.
Yeah, sure, yeah, 950.
Okay. So for anyone who's sitting there staring at the wall, what do you think? What do you think would be a more useful use of your time right now? Follow along and do the calculation. Okay, yeah, mine does too. 5.9. All right. So let's do it like that then. If you get a different answer, let me know. Let me know. I'm sure there's calculators that won't give the same answer, but
What was the last one,
there you go. Easy.
eh? Change the batteries.
But it's not even solar power. So that's going to give me an answer of 5.9 ohms. So that's my total resistance using our resistance in a parallel circuit formula that we did yesterday. So then I can put my 5.9 back into this formula here, right? So V squared over R. So my voltage is 100. And my R is 5.9. So if I do 100 squared divided by 5.9, I get 1685. Look at that. Geniuses. Isn't that amazing? And what was the third way that I said we could do it? Oh, we can work out our total current. Or we work out current in each branch, add those together to give us that total current. Oh no, not even that. We could just go resistance. How do I work out my total current? I'm going to go total voltage divided by total resistance. Total current equals total voltage divided by total resistance. So that would be 100 divided by 5.9, which should be like 16 or something like that. 16.9. And then I use my current. I just go P equals I times R. P equals I times V. So 16.9 times 100 equals 1690. That's simple enough, right? Roughly the same thing. I mean, it might seem quite different, but when you look at the number, that's like 0.025% or something. Tiny. Okay. Am I making enough sense? Am I making any sense? It's all right. We'll keep pushing through. We will do plenty of practice. Trust me on this one. If you take nothing else out of this, practice. We will do practice all afternoon. Yes. We'll stop for lunch because it's lunchtime, and we'll do that when we come back. But yes, we can do current in each branch. It's a good idea. So I might push through this quite quickly, but I'm doing that so we can get to the practice bit, and then we're just going to do it. So going hand in hand with practice is actually following along and doing this, right? So I can already see the people who are doing that, the ones who are curious and they're getting their calculators out and doing it, they're starting to pick up, oh yeah, okay, I get this. And then some of us are just sitting there going, oh yeah, he'll tell me what to do. And then you're watching me do it and go, how did he do that? So follow along with your calculator and do it. So let's break for lunch. Let's have 45 minutes. Come back at 1:45. Thank you, team.
I'll tell you what.